For those of us interested in the deepest and most fundamental rules of the universe, there are two things we need to know about. One is to identify the smallest building blocks of matter, and the second is to know about the forces that hold them together. While we know of several forces that govern the subatomic world, the strongest of them all is called, rather unimaginatively, the strong force. Now we have to be careful because it's easy to be sloppy in our language. In the 1950s, we used the term strong force to mean the nuclear force, and it probably won't surprise you to know that I made a video on why scientists determined that the nuclear force even existed. But in the last 40 or 50 years or so, we've come to understand the strong force in a different way. To begin with, we know that the tiny protons and neutrons at the center of atoms are made of even smaller particles called quarks. Quarks were proposed in 1964 and proven to be real in the 1970s. The existence of quarks is well-established science. Because protons and neutrons are found inside the nucleus of atoms, we call them by the overarching and generic term nucleons. That's basically like how we can distinguish men and women and yet combine them too and call them by the single term human. Each nucleon consists of 3 quarks. That's a simplified picture of what's going on inside, but it helps us understand the key points. You can think of a nucleon as a tiny sphere with a radius of about a quadrillionth of a meter across. The quarks zoom around inside the sphere, traveling at nearly the speed of light. And if you have particles moving at that outrageous speed, in that ridiculously small volume, you have to have an ultra-mega strong force holding it all together. And because we're talking about the realm of the super tiny, the force governing the motion of quarks has to be a quantum force. Now, I've made lots of videos on quantum forces. If you're interested in the subject matter, I recommend watching 4 other videos on quantum field theory, Feynman diagrams, perturbation theory, and quantum electrodynamics. But I can give you the high points here. The simplest of the quantum theories is called quantum electrodynamics, or QED. That theory talks about how electrically charged particles interact by shooting photons back and forth between each other. The simplest interaction occurs when a charged particle, like an electron, emits a photon and then recoils. Now, the force holding the quarks inside nucleons work a little differently. First, the relevant charge is not the electric charge, but the strong force charge, what physicists call color. I talk about quantum color in yet another video, but color in this context is basically a different kind of charge. It has nothing to do with color in the normal sense of the word. Sorry about that, by the way. My tribe of particle physicists do have an idiosyncratic way of naming things. In any event, unlike electric charge, which comes in 2 varieties, plus and minus, the strong charge comes in 3 varieties, named red, blue, and green. Again, nothing to do with regular color. The particles that the colored quarks exchange are not photons, but rather particles called gluons. The photon is the particle of the electromagnetic force, and the gluon is the particle of the strong force. And, in analogy with QED, or quantum electrodynamics, we call this theory QCD, for quantum chromodynamics. Get it? Chromo, color? All right, sometimes I'm a little embarrassed by my tribe. For those of you who are fans of Feynman diagrams, we draw an exchanged photon as a wavy line, while a gluon is a corkscrew. And, just like all Feynman diagrams, the Feynman diagram of 2 quarks exchanging a gluon corresponds to an equation that a sufficiently diligent student can solve. But it's pretty hard, so kids, don't try this at home. So how is QCD different from QED? Both involve exchanging force-carrying particles between other particles carrying charge. The photon is massless, the gluon is massless. The photon has no electric charge. The gluon has, oh, wait a minute, there's a difference. Gluons carry the strong charge. They have color. And that little difference has a huge consequence. Because gluons interact with colored particles, gluons can interact with other gluons. That's way different than 2 photons, which are completely oblivious of each other's existence. And it qualitatively changes the behavior of the strong force. Let me explain. If you have 2 magnets and kind of play around with them, you quickly find out that they feel a stronger force between them if they're close to one another and a weaker force if they're far apart. That's how the electromagnetic force works. On the other hand, if you have a rubber band, you find that the 2 ends don't feel much of a force when the band isn't stretched. But As you stretch it, the force gets stronger and stronger. This pulls the quarks back into the nucleon, and that explains why quarks don't just get knocked out of nucleons at low energy. Now, as it turns out, if you smack a quark hard enough, you can send it careening out of a nucleon. But the force between the quark and the rest of the nucleon acts like a rubber band that is continuously stretching. Sometimes we call this a string of color force. And if you hit the quark hard enough and stretch the string enough, you can eventually break the string. But here's the tricky thing. When we break it, the energy that was stored in the string converts into matter and antimatter, specifically quarks and antiquarks. This process can go on for a while with more stretching and breaking and creating quarks and antiquark pairs. In the end, the particles all pair up, and what we get is a bunch of particles all traveling more or less in the same direction as the quark that got knocked out of the nucleon. Physicists call this blast of particles a jet. And we see jets all the time. Here is a picture of a real event collision in the CMS detector, one of the big LHC experiments. See those sprays of particles? Those are jets. So those are the big ideas of quantum chromodynamics. The strong force has a different charge and a force-carrying particle than quantum electrodynamics, but in some respects they aren't so incredibly different. The big difference is the fact that the force-carrying particle is itself charged with, as we have seen, dramatic consequences. The subatomic realm is really a pretty crazy place.